in November 1915. 1 month later, December 22nd, 1915, he received a postcard from Karl Schwarzschild. Karl was the director of the Potsdam Observatory, but he was also a German patriot. Both Einstein and Karl were German Jews. The difference between them, Einstein was a pacifist, Karl was a patriot. He volunteered to go to the German front, but as he was there, he derived the solution that we now know as a non-rotating black hole, the Schwarzschild solution. And he sent it in a postcard to Einstein. And Einstein was very excited by this derivation because he thought that his equations are so complicated that it would be very difficult to derive an exact analytic solution. And so he, a month later, communicated this result to the Prussian Academy of Sciences. And the tragedy here is that Karl died 6 months later at the German front from a rare disease. And the lesson I draw from this is that if you want to work out the consequences of a theory, you better be a pacifist. And I would like also to advertise a book that was written by Marsha Bartusiak and fresh off the press, came out in print just a few months ago about the history of black holes. One aspect of that history is that in 1939, when Einstein was a professor here at the Institute, he wrote a paper arguing that black holes do not exist. And his argument was that if you let a star collapse, if the star has a little bit of angular momentum, some spin, eventually that would prevent the star from making a black hole. He submitted this paper around the same time that Oppenheimer and Snyder derived their solution. I'm not sure if he was aware of that, but clearly his argument is wrong. First, you can imagine an idealized problem where the matter just falls straight in the radial direction to make a black hole, and we shouldn't rule out concepts, as Einstein was well aware of when he was younger, just based on practical considerations. And the second thing is that obviously when we look at water running down a faucet or a bathtub, we see that angular momentum can be transported, and the water ends up in the drain. So in principle, black holes could be made. And I would like to highlight the Princeton Connection in the history of black holes. Of course, Princeton was a very important place for the history of black holes, obviously starting with Einstein that was here, and he had postdocs, Nathan Rosen, Robert Oppenheimer, the director of the Institute, derived the first solution for a collapse of a star that could lead to a black hole. He was not very proud of that. He tried to dismiss astrophysics later on in his career, saying that it's an environmental science, but actually he is remembered very much for this derivation. John Wheeler coined the name black hole. He had a school of postdocs and students. And the way I see him is as a visionary. And the reason I would like to highlight that is because it's not just about the math. Physics is not about the math. It's about having the right intuition and understanding which objects may exist in reality given our theories. And Wheeler had that. And in a way, the way I view him is as an architect. He had an architect obviously needs an army of engineers that will derive the results from the equations, but Wheeler was not a very mathematical person. He had the vision. And the group of people working with him derived all the important results. And some of the names were mentioned yesterday. Bekenstein was one of his students, derived black hole entropy, and Wheeler commented that the idea is so crazy that it might be real. And Christodoulou derived the memory effect that we heard about yesterday, naked singularities. And of course, there was the group of astrophysicists that many of us are familiar with, some are in the audience, that worked on black holes in the astrophysics context. And more recently, simulations of black hole mergers that I'll speak about started giving useful results with the work by Franz Pretorius in Jadwin. And the quantum aspects of black holes are very much still a puzzling area of investigation. Juan Maldacena will speak about the connection between quantum physics and general relativity later on today. So why are black holes fascinating? Aside from the fact that they are very peculiar distortions of space-time, and I actually gave a talk about mostly exoplanets to the class of my daughter, and at the end I put one slide on black holes, and the children in that class were extremely excited just on the issue of black holes. And one of them was asking me, what happens to a person as it falls into the singularity? And I started describing the way that his body will be torn apart, and then the teacher stopped and said, they will have nightmares, please don't continue. So why is it that we are so fascinated with black holes as physicists? The reason is that they represent a breakdown of general relativity. And one of the advices I give to young people is that, when I hear talks of people describing results in cosmology, for example, and putting better and better limits on deviations from the standard model of lambda CDM, I get quite bored in these talks because physics is driven by anomalies. You are really after things we don't understand. And just focusing on things we understand to better precision is not exciting. And so the reason black holes are exciting is because we don't understand something there, and that's the singularity. Clearly, Einstein's theory of general relativity is incomplete. And we know why it's incomplete, because it doesn't incorporate quantum mechanics. And so there are two types of singularities that we know about in the real universe. One is the Big Bang, and the second is black holes. The problem with the Big Bang, as we heard by Matthias, is that we had inflation in between us and that time, if it ever happened. And the inflation obscures our view of the Big Bang. We can't really go back in time because the universe inflated, and we can't look through inflation to see what happened prior to that at the singularity. And so we are left with black holes as a test bed where we can test the unification perhaps of quantum mechanics and gravity. And a number of puzzles that we would like to address. Black holes, we know, possess qualities similar to elementary particles. They have a mass, a spin, and a charge. And in fact, Einstein thought at some point that perhaps these elementary particles are black holes. So when matter falls into a black hole, is information lost? If we describe the final object by 3 numbers, obviously some information must be lost, but perhaps not. And of course, in the semi-classical approximation, there is the Bekenstein-Hawking radiation. There is a lot of debate these days about whether it exists or not, and what does it really mean. And for astronomers, it would be interesting to think about whether quantum effects are imprinted on the scale of the horizon. It's quite unlikely, but we should check. It was unlikely in the minds of many people that heavy objects fall at the same rate as light objects, but Galileo checked it. And of course, there are the questions about cosmic censorship, whether we are protected from the singularity under all circumstances, because if this breakdown of general relativity is not hidden behind the horizon, then it's a much more serious issue, because the rest of the universe is affected by what is happening near the singularity. And so, as a result, we would like to make sure that indeed everything that happens in cosmology is not affected by what is going on close to the singularity. And the no-hair theorem is, of course, another important question of whether black holes have other numbers that describe them other than mass, spin, and charge. So as a practical astronomer, an interesting question to ask is, how do we make a black hole in our backyard? Can we actually imagine doing so? Well, there is a very simple prescription for that. You just need to fill the orbit of Jupiter with water. So here is the sun, and if you just sprinkle in water, here is Jupiter, and fill up the entire volume with water, you'll end up with a black hole that weighs 1 billion solar masses. The only problem is, being practical, is that you need more water than the Milky Way has. But other than that, and the other thing, of course, is that when you try to spray the water into such an object, you could get 100 trillion solar luminosities out. So you can easily get burned in the process. Don't try it at home. But a black hole represents this ultimate prison out of which nothing can escape. Even light cannot escape from within the Schwarzschild radius, which is twice Newton's constant times the mass divided by c squared, the speed of light squared. And the amazing thing is that the universe made objects like that, 1 billion solar mass black holes, already less than 1 billion years after the Big Bang, when the universe was just 5% or so, 7% of the present age. So when we look at the universe, what kind of black holes do we see? Well, there are two main classes. One has to do with the collapse of stars, whose understanding was pioneered by the work of Oppenheimer here. And so when massive stars consume their nuclear fuel, they lose pressure support, and the core of the star collapses to make a black hole, if it's massive enough. So that's one category. And here the mass is somewhere between 3 to 10 solar masses typically, but it could be much larger than that depending on the progenitor mass of the black hole. And then there are supermassive black holes at the centers of galaxies, where gas is being funneled to the center of the galaxy. It seems to be a generic result of galaxy formation. We see black holes like that in almost every galaxy that we look at. In between them, we are not sure. There may be black holes that are in the intermediate mass range between a few solar masses and 1 million solar masses. There are some indications that they may exist, but we are not 100% sure yet. And then there is the possibility of primordial black holes, tiny microscopic black holes that may have been formed in the early phases of the universe due to density perturbations of order unity, either during phase transitions or other processes that we don't fully understand. And I'll speak about them. The interesting thing about the black holes that we see is that there is a lot of similarity between black holes across a wide range of masses. So when you look at black hole binaries that are associated with a normal star serving as a companion that donates mass to a stellar mass black hole, you often get jets. These are called microquasars or microblazars that look very much like the jets we get out of 1/10 of all the supermassive black holes that we see in the universe. And you can just scale up the length scale, the time scale, by the mass of the black hole. You end up with very similar structures. And in fact, even without the companion, you often get gamma ray bursts from very massive stars. That's when the core of the star collapses to make a black hole, and then the black hole produces, the accretion disk around the black hole produces jets that drill a hole in the envelope of the star. Quite remarkably, we can see them to cosmological distances, and we expect the physics of jet production to be quite similar because the geometry is quite similar. Now, if we imagine an isolated black hole and getting close to it with a flashlight, just pointing the flashlight in different directions, you would get the propagation of photons to follow curved trajectories. And of course, photons propagating towards the black hole will get absorbed by it. But if you sit at the photon orbit for a Schwarzschild black hole at 3 gm/c², you can look straight and see your back because the photon makes a complete circle around the black hole. the question is, can we map observationally the space-time around black holes and perhaps learn about deviations from general relativity? One way to do so is to consider the supermassive black hole at the center of our galaxy, Sagittarius A star, and map the space-time by sending precise clocks to that space-time, pulsars. We heard about pulsars yesterday from Vicky Caspi. And so one can imagine that pulsars may exist in the vicinity of Sagittarius A star because we see a lot of stars there. And then in a paper we wrote about a decade ago, we suggested perhaps looking for pulsars very close to Sag A star as a way of mapping the space-time. This is a very difficult task, as Vicky pointed out. But there was one magnetar that was discovered about a parsec away from the center. It's not close enough to test general relativity, but there are ongoing searches for more pulsars. And of course, one thing to check is, for example, whether the quadrupole moment of the central black hole matches what we expect based on the inferred mass and future inference of the spin of this black hole. And any deviation of the quadrupole from what we expect would be a test of the no-hair theorem. Another way to map the space-time around black holes is, of course, using gravitational waves. And we heard quite a lot about it yesterday. And the statistics of seeing black hole binaries with advanced LIGO is quite promising. We should be able, there is a wide range of possibilities because we have only a few systems known of, for example, neutron star binaries. We don't have any that we know about of neutron star black hole or black hole systems, but the estimates, the more realistic estimates are that we will see tens of those types of binaries with advanced LIGO once it's completed. Another way to map the space-time is, of course, to consider a supermassive black hole that has a low-mass black hole companion that is orbiting, let's say, in a circular orbit around it. This companion could have been formed in an accretion disk, just like planets form around a star in a protoplanetary disk. And having, for example, a low-mass black hole orbiting a high-mass black hole can allow us to map the space-time if we detect the gravitational waves from that with ELISA. So that's another way of mapping the space-time around the black hole, but it's more for the future. Right now, actually over the past 2 weeks, there were 5 papers on AstroPH, the archive, discussing the latest constraints from pulsar timing arrays. And unfortunately, yesterday, Vicky did not have much time to discuss it. But the current constraints are quite remarkable in the sense that there are theoretical predictions as to what black holes would produce. For example, 2 galaxies come together. If they have black holes at the center, the black holes will make a binary, and the binary will eventually coalesce. And as a result, there would be emission of gravitational waves, as you can see in the video on the left. But the point is that if you sum up the emission from all the galaxy mergers in the universe, there are various models for that. For example, you can see here in the gray line and the green line or the blue line, different models for how large should omega in gravitational waves be at a frequency of about a nanohertz, 10 to the minus 9 of a hertz, corresponding to the observing time of several years, up to 10 years. The idea is that if you have a pulsar and the Earth is being moved around by a stochastic background of gravitational waves, as a result of that, we would lose timing synchronization with these pulsars in a coordinated way because there would be a quadrupolar change in the space-time around the Earth that we could, in principle, detect. And the current limit is actually below the typical values that all these theoretical models predict, assuming that black hole binaries coalesce due to the emission of gravitational waves. If there is a lot of gas, for example, in the vicinity of binary black holes, then the inspiral of the black holes would be much quicker, and as a result, you would get less emission of gravitational waves. So it's quite remarkable that right now we have already reached the point where there is a need for some other mechanism to drive the black holes together that is more efficient than gravitational wave emission at a frequency of about 1 nanohertz. And another exciting result of the last week, if you take the current limits on the stochastic gravitational wave background, you can calculate the strain amplitude, the perturbation due to the gravitational wave, in terms of the black hole mass, distance, and for a particular frequency. So if you freeze the frequency, the strain goes like the mass to the 5/3 power, and then you can make a plot of how large should this strain be as a function of the mass of the black hole. If we look at all the black holes we know about in our vicinity, out to a distance of order 100 megaparsecs, what you find is that the current limits already rule out equal mass companions, or even better than that, a mass ratio of 1 to 10 for all the black holes that we see, all the way to 100 megaparsec, because we would have seen a periodic signal in the direction of these black holes by the pulsar timing arrays that are now functioning if they had binary companions. So that's quite remarkable, that we can actually limit binary black hole systems in the nearby universe based on, it also implies that, you know, in the relatively near future we might detect something. But the easiest way to probe the space-time around black holes is using electromagnetic radiation, just because it's so easy to detect. And of course, using electromagnetic radiation has two aspects. One is testing the theory of gas hydrodynamics in the vicinity of black holes. We had this theory since the middle of the 60s, and we would like to test it directly. And of course, we can test general relativity. And the nearest black hole is the one at the center of the Milky Way, Sagittarius A star. It's inferred to have a mass of about 5 million suns at a distance of 24,000 light years. And not only that we infer its existence from the motion of stars around it, just like the motions of the planets around the sun allow us to infer the mass of the sun, we also see gas clouds orbiting the black hole and being torn apart in that process, sort of like watching an infant being fed. And it gives great satisfaction for astronomers to see things in real time. We're not talking about billions of years, but years, actually, in this process. And the amazing thing about Sagittarius A star is that it's the largest black hole on the sky. So if you wanted to resolve the vicinity of a black hole, this would be an ideal candidate. One way to resolve the space-time around the black hole would be to send a technician. And you're all familiar with this technician from the commercial of Verizon that asks, "Can you hear me now?" going with his cell phone. And of course, if this technician is sent close to Sagittarius A star, his image will get redder. And at some point, we won't be able to hear him. Actually, nothing bad will happen to his body when he approaches the horizon, because even though the gravitational acceleration is almost 1 million times that on the surface of the Earth, 1 million times g, there is not much tide across 2 meters of his height. So he will only suffer as he gets closer to the singularity 10 minutes later. And here is an illustration of how a light beam that is orbiting around the black hole would look like to an observer depending on the orbital plane. So as we change the inclination of the orbital plane, you realize the image changes. And generally speaking, one gets 2 images due to gravitational lensing when this flashlight goes behind the black hole. On one side, the image is brighter because of the Doppler effect. As the light source approaches us, it's brighter. And on the other side, it's dimmer. there is this central region which is the shadow, the silhouette of the black hole, due to the fact that light gets absorbed when it enters the horizon of the black hole. And so we can aim to resolve this image for Sagittarius A star. And of course, the image is, as I mentioned, made of several components. One part is just the direct light coming from that source, from the hotspot. There is a second image due to light passing around the black hole and coming to us. And then there is another image due to two passages, but they become fainter and fainter as you require more and more passages around the black hole. And one can do hydrodynamic simulations and trace the light rays around the black hole to see what a real image would look like. I should mention that the image that I show here depends on the inclination of the orbital plane, but also on the spin of the black hole. So the hope is that you can measure not just the mass of the black hole, but also the spin. And this is a result from a hydro simulation that includes turbulence. So you can see pretty much the same eye of the shadow of the black hole, but there is some fuzziness to the image due to turbulence. There are three fortunate coincidences. So nature is not always kind, but in this case, it was very kind to us, and we should take advantage of it. The three coincidences are that right now, Sagittarius A star is not fed much. It's basically starved. So there is very little gas falling onto it, which means that we can actually see through that gas. The gas is transparent to synchrotron self-absorption as long as we observe that gas at wavelengths shorter than 1 millimeter. That need not be the case in general. You know, there were periods of time when there was much more gas accretion. We wouldn't be able to see through at those times. The other interesting coincidence is that the interstellar medium allows us to see the image of Sagittarius A star on the scale of the horizon. There is not much blaring, once again, as long as you work at wavelengths shorter than 1 millimeter. And finally, if you ask, suppose I have a telescope as big as the Earth, and I operate, and I would like to actually resolve the horizon of Sagittarius A star. What is the wavelength that you need for that? From our optics classes, we know that it's the wavelength over the diameter of the telescope gives you the angular resolution, so you can figure out what the wavelength is, and it turns out to be 1 millimeter. The only problem is we need to build a telescope as big as the Earth. Can we actually do that? Turns out there was an undergrad doing a senior thesis on this problem with Wheeler that concluded, no, it's not feasible. And then he moved on to work on some other condensed matter problems. Well, I actually contacted that undergrad and told him that it's feasible now. Too bad that he shifted to another field. And we can do it with long baseline interferometry at sub-millimeter wavelengths. So the idea is that you don't have a full dish of a telescope that covers the Earth, but you do have stations scattered around the Earth, and that allows you to reach the angular resolution that you need. And these are various millimeter wavelength observatories throughout the Earth, as seen from the direction of Sagittarius A star. So if you were to sit at the galactic center and look at the Earth, that's how it would look like. And right now, 3 of these observatories were used already, and 2 more are being added to this array. So here are the 3 that were used. And the constraints that were reached with them are, of course, we don't have an image, but we have constraints on the image. So we already know the characteristic size of the silhouette. And that seems to indicate that the spin of the black hole is not large right now. We can also look at another black hole, which is about 1,400 times more massive than Sagittarius A star. It has a mass of 6 billion suns, but it's at a distance that is roughly 2,000 times farther than Sagittarius A star. And the ratio of these 2 numbers is of order unity, so we can, in fact, resolve its image similarly to Sagittarius A star. The interesting point about this one is that this is the black hole in M87, a giant elliptical galaxy. it has a jet coming out of it. So if we image the shadow, we can understand better how jets are launched from the black hole vicinity. And here are theoretical calculations of what we might see if we were to resolve the shadow. There is the shadow and then the base of the jet, which very much depends on physics we don't fully understand. I should mention that we already have some data on that, and that's a paper written a few years ago by Shep Dolman and collaborators. And the size of the shadow in that case happens to be smaller than the innermost stable circular orbit around a non-spinning black hole. And that implies that the black hole must be spinning. There are other arguments why black holes that show jets are likely to be spinning, but we have now direct evidence for that. Now, speaking about supermassive black holes, how do we make them so early in the universe, and what effect they had on the rest of the universe? This is a simulation, a cosmological simulation starting from cosmological initial conditions. What you see on the left is what you would get if the gas would just flow to dark matter concentrations and heat up due to the hydrodynamics. What you see on the right is the effect of the black hole energy injection into the surrounding gas. You see that like fireworks, explosions taking place because we are going over long time scales. These explosions typically take tens of millions of years, but on the cosmological time scale, these are very short energy injections episodes. And the popular seeds of the black holes are now considered, there are many papers on this scenario, are considered to be large gas clouds that manage to collapse sort of like supermassive stars to make the seeds of these quasars early on. I should reiterate that these quasars have roughly 100 trillion solar luminosities coming from a region comparable to the orbit of Jupiter around the Sun. And we see supermassive black holes also in the nearby universe. In fact, they appear to be, the mass that they have appears to be correlated with how big the galaxy, the host galaxy is. And in particular, the mass of the black hole is correlated with the luminosity of the spheroid of stars that surrounds it. In this plot on the left, we see black holes all the way up to more than 10 billion solar masses. And on the right, you see the correlation with the velocity dispersion of the stars that characterizes the depth of the gravitational potential well in which the black holes are embedded. Now, if we were to consider, this particular correlation may result from the fact that black holes release so much energy that eventually they unbind the gas from the galaxy that fits them. And so they cannot grow beyond a certain point that depends on the depth of the gravitational potential well in which they are embedded. And so black holes are able to grow to a higher mass if they're embedded in deeper potential wells or in more luminous galaxies. That's the general popular view. And of course, if each galaxy has a black hole at its center, when galaxies come together, these black holes would make a binary. And we see snapshots of this process in action. We see centers of galaxies at separations of order 30,000 light years, roughly the size of the Milky Way galaxy. And we see some that are at separations of a few light years, or a few thousand light years. And this is taken from the Sloan Digital Sky Survey, and you can see this beautiful photo album of galaxies in the process of merging. We also see examples of two centers of X-ray emission in some galaxies where the black hole is obscured by very dense clouds of gas and dust. And we can see through that gas only in X-rays. There are some beautiful examples of radio-emitting black holes where you see jets coming out from a binary from two centers of light, so to speak. And one interesting point is that if the two black holes make a tight binary, then as the binary tightens due to the emission of gravitational waves, the orbital period gets shorter. And so if there is a jet, the jet would precess on the sky with an ever-increasing rate, and sort of like the chirp of a cricket. And so you could look for binary black hole systems if one of them has a jet coming out of it in the form of radio crickets, where the jet would spiral around with an ever-increasing frequency as you go towards the base of the jet. Here is an example of two black holes separated by about 20 light years that have a total mass of around 1 billion solar masses observed in the radio. There is also an example from this year of potentially a binary being detected in the light curve of a quasar at a redshift of 0.3. This was interpreted by a group from Columbia University just a couple of months ago as being due to the Doppler beaming effect, where the flux is modulated due to the fact that the emitting source is moving around with a speed that is quite substantial, of the order of 1/10 of the speed of light. One can imagine more than just two black holes. As we well know from experience with humans, when you have more than just a binary system, the system is unstable. And if the binary does not coalesce before a third galaxy comes in, you can get, through galaxy mergers, triple black hole systems, or even more than 3 black holes in one system. And as a result of that, one of the black holes gets shot out of the galaxy at a very high speed, thousands of kilometers per second. So one way to get wandering black holes in space is due to this slingshot effect. There is another way to kick a black hole out of a galaxy. When two black holes come together, if they don't have exactly the same mass, you can think about the problem as the small black hole orbiting the big black hole. And then eventually it gets to the innermost stable circular orbit and plunges towards the massive black hole. And at that point, the emission of gravitational waves is beamed in a preferred direction because of the final plunge. As a result of that, there is a rocket effect. Momentum conservation implies that the remnant black hole would move in the opposite direction. And so you get a recoil. Since the early 70s, there was work by Bekenstein back then. People wondered what exactly should be the level of recoil. It was not easy to calculate because we are talking about the final plunge where the spacetime is distorted quite significantly. The problem was solved numerically, thanks to the pioneering work by France and other people, Saul and collaborators. And you saw it on the left here. People are able to solve now the merger of two black holes and get the kick, the recoil of the remnant black hole. It's at the level of, the characteristic level of 100 kilometers per second for non-spinning black holes, up to 200 kilometers per second. Or if you add spins to the two black holes, you can get up to 4,000 or 5,000 kilometers per second, well above the escape speed from a galaxy like the Milky Way. Do we see things like that in the sky? Quasars flying off from galaxies. Here is an example. 2 centers of light, one of which is moving away from the center of the galaxy at about 1,000 kilometers per second. Another possibility is that, as we all know, the galaxies form hierarchically. They are made of building blocks that were formed early on in the universe. So there is the hierarchical process of making galaxies, starting from small galaxies, becoming bigger and bigger as they merge. And if that's the case, and if each galaxy along the way had a black hole at its center, when 2 galaxies combine, they make a black hole binary that eventually gets a recoil. Now, the early building blocks of the Milky Way were much shallower potential wells. And so the kick that a black hole would get from this merger would remove the black hole along with some stars from the center of the dwarf galaxies that made the Milky Way halo. So you might think, well, if the typical kick is 100 kilometers per second, all these building blocks of the Milky Way halo would leave behind. Someone is calling my Apple phone right now. So there might be black holes floating in the Milky Way halo due to this process. And one way to search for them would be to look for the star clusters that they took with them as they were removed from these dwarf galaxies. And one can calculate that there should be 100 black holes wandering in the Milky Way halo. And these star clusters are quite different from the normal star clusters, like globular clusters, because they have a central black hole that dominates the mass. And the amount of light in stars is much less than the amount of mass in the black hole. And you can easily identify those if we can just find them. So we actually looked through the Sloan Digital Sky Survey. There are some candidates for spherical star clusters at redshift 0 that might be candidates for recoiled black holes. But one has to take spectra of those to figure out if indeed their inner structure is consistent with a central dark point mass. Another interesting outcome from black hole binaries is the possibility that when two black holes come close to each other, they scatter stars. And in fact, they scatter stars in such a way that their orbit becomes eccentric. There were many studies of that illustrating that as the black holes scatter stars, their eccentricity is likely to grow. And if that's the case, when they pass close to each other in an eccentric orbit, they can kick out stars at very high speeds. And in fact, you can get stars ejected from galaxies close to the speed of light. That's quite remarkable. The universe may be filled with a sea of stars moving close to the speed of light. We haven't seen any. This is a theoretical prediction from a year ago. And how many stars would we expect? If you just go through the math of the rate of galaxy mergers, you find that within the Virgo cluster, the cluster of galaxies that we are on the periphery of, there should be 10,000 stars moving faster than a tenth of the speed of light. How easy it is to detect them? Well, with different instruments, we might be able to see some of these stars with the next generation, for example, of telescopes. So that's quite exciting. The other interesting point is that we've been using in cosmology mostly photons to study the universe. Photons move at the speed of light. These stars can move at arbitrary speeds. So in fact, we can probe cosmology in a different way. It takes different amounts of time for stars to reach us compared to photons from a distant galaxy. So in fact, all the relations that we are used to in cosmology are changed if you were to consider those stars. The speed of the stars is declining as 1 over the scale factor because you can think of it as the de Broglie wavelength is being stretched by the scale factor. And as a result of that, the relation between co-moving distance and time of travel is changed relative to photons. There is an extra factor of 1 over the scale factor in this relation for these massive stars, which are just like massive particles. And then, of course, there is a Doppler boost if you were to look at a star moving towards us. And so, and finally, there is the possibility of gravitational deflection of those stars, similarly to gravitational lensing. The deflection is much more significant because it scales as 1 over the velocity squared. And so these stars moving less than the speed of light suffer great deflections as they move near galaxies. It's just another probe of cosmology. Over the past 5 years, there was a flurry of papers on the possibility that a star may get tidally ripped apart by a black hole, supermassive black hole. There was some previous history to this field, but it's actually exponentially growing over the past few years. And if you consider the sun, if the sun were to approach Sagittarius A star, the center of our galaxy, within 10 Schwarzschild radii, the sun will become a spaghetti-like stream. It will be stretched into a thin filament of gas and eventually make an accretion disk around the black hole and feed it. Such a process takes place once every 100,000 years in the Milky Way due to scattering of stars off each other. And for black holes more massive than 100 million suns, this process doesn't take place because the black hole is so big that it swallows the star whole. So this process is, in effect, only for relatively low mass supermassive black holes. And the feeding rate is huge. Basically, you get a fraction of a solar mass within an pericenter crossing time, which gives you a feeding rate which far exceeds the limit, the so-called Eddington limit for black holes by a factor of 100 or 1,000. And here is a computer simulation of a star being shredded to a spaghetti-like filament. And as it comes back, it establishes some accretion flow around the black hole. So that's one way of feeding black holes and allowing dormant black holes that do not shine brightly to flare up. There was actually a jet observed by Ashley Zauder, that must be in the audience, and others and collaborators, from one of these tidal disruption events at cosmological distances. And the interesting point here is that if the black hole has a spin, the orbital plane of the star that gets disrupted has no relation to the spin of the black hole. It's arbitrary. And so you end up getting an accretion disk. And the question is, will the accretion disk align itself with the spin of the black hole? In other words, will the jet come out in the direction of the spin of the black hole? Or will the jet be perpendicular to the original orbital plane of the star? And if it were, you could get precession. And that would introduce, just like in a pulsar situation, you will get a pulsating flare. It will be a pulsar in the context of a quasar. We haven't seen that in this case. And from that, we deduced with Nick Stone that presumably the jet came out in the direction of the spin of the black hole. And this question was unsolved theoretically. You can also disrupt a star in a black hole binary. And here you see in the rotating frame and in the inertial frame how the star gets disrupted. The interesting point here is that if you get flares like that, separated, let's say, by 10 years, you could tell that the binary gets tighter by the emission of gravitational waves. So it's one way of inferring the inspiral of binaries. Let me just say a few words about primordial black holes and close with that.
A few words.
Yeah, OK. So in this case, primordial black holes are produced by density fluctuations of order unity on the scale of the horizon. And in principle, you might wonder, maybe they are the dark matter. We see dark matter that doesn't interact except gravitationally. Hawking evaporation would last longer than the age of the universe as long as the mass is well above that of an asteroid. An interesting point is that the size of the horizon for an asteroid mass black hole is roughly the size of a proton. That's the Schwarzschild radius of an asteroid mass black hole. The gravitational tidal force is comparable to the strong force in this case. A surgical passage of a black hole, low mass black hole, if they make the dark matter, for example, these primordial black holes, a passage through the Earth would not leave much of an impact. It will just excite some seismic waves, and it would be very difficult to detect those. So can we actually rule out the possibility that the dark matter is made of primordial black holes? As it turns out, Saul Tokolsky, in work with Bill Press, dates back to 1972, considered the following thought experiment. Imagine you have a spinning black hole, and you're surrounding it with a spherical mirror. Any bosonic field, like a photon field, could get amplified, they showed, by the spin of the black hole if the frequency of the radiation is less than the spin period. And now, because of the mirror, you end up getting a cavity similar to a laser where you get this super radiance amplification of the wave until this cavity explodes. You end up with a black hole bomb. Nowadays, nobody would call it a bomb because that's politically incorrect. But back then, black hole bombs, you could publish a paper with this title. Anyway, do we have situations like that? Well, the answer is yes. In cosmology, if you make a primordial black hole early on in the universe, it's surrounded by a plasma. When you put a photon in a plasma, it acquires a mass. It's the plasma frequency. A mass is equivalent to a mirror. What happens in a mirror is that the light bounces back because its frequency is below the plasma frequency of the metal that reflects it. The same thing happened in the early universe. You can show that if these primordial black holes had a little bit of spin, you would end up with black hole bombs. And that would distort the cosmic microwave background. And so when you consider the limit from COBE and the future limit from Pixie, you can actually rule out the possibility that the dark matter is made of primordial black holes as long as its mass is more than the mass of the moon. The mass of the black hole is more than the mass of the moon. The fraction has to be far less than unity. Okay, so that's just from the spectral distortion of the cosmic microwave background. And then the rest of the mass range can be ruled out by considering the capture of primordial black holes by neutron stars. Neutron stars would not exist if a primordial black hole would sink to their center and start accreting the neutron matter. And one can show that this sets a very tight constraint on the fraction of the dark matter that is in primordial black holes with masses between an asteroid and the mass of the moon. So it basically rules out the entire range of masses above the mass that Hawking radiation would eliminate those black holes. So I would say with these results, the dark matter is not likely to be made of primordial black holes. So let me just summarize. I talked about various windows towards mapping the space-time around the black holes. And in particular, gravitational waves are a very exciting probe that perhaps in the next few years will allow us to probe the space-times of black hole binaries. Direct imaging, of course, is also very promising within the next few years, either of Sagittarius A star or M87. And black hole binaries that are being discovered through their electromagnetic radiation, they can in principle accelerate relativistic stars throughout the universe. And the coalescence of these binaries results in recoils, quasars that are offset from their host galaxy, either in velocity space or in position. And one can get tidal disruption of stars that as another probe of these black holes. Primordial black holes, unfortunately, cannot make the dark matter. Thank you.